Welcome to today's paper reading. Today's paper is titled, Gaussian Frosting, Editable Complex Radiance Fields with Real-Time Rendering. This paper was published on AR14 by Antoine Guédon and Vincent Lepetit from LIGM, École de Ponce, Université Gustave Eiffel, CNRS, France. The authors introduce Gaussian Frosting, a new mesh-based representation designed for high-quality 3D rendering and real-time editing of complex effects. This approach builds upon the 3D Gaussian Splatting framework, which optimizes a set of 3D Gaussians to approximate a radiance field from images. The method begins by extracting a base mesh from these Gaussians during optimization. An adaptive layer of Gaussians with variable thickness is then built and refined around the mesh to better capture fine details and volumetric effects near the surface, such as hair or grass. This layer, termed Gaussian frosting, is analogous to a coating of frosting on a cake, with the thickness of the frosting corresponding to the fuzziness of the material. The authors also introduce a parameterization of the Gaussians to ensure they remain within the frosting layer and automatically adjust their parameters during mesh deformation, rescaling, editing, or animation. This representation enables efficient rendering through Gaussian splatting and supports editing and animation by modifying the base mesh. The effectiveness of the method is demonstrated on various synthetic and real scenes, showing superior performance compared to existing surface-based approaches. Additionally, the authors plan to release their code and a web-based viewer. Figure 1 illustrates the proposed representation of surfaces using a mesh covered with a frosting layer of varying thickness composed of 3D Gaussians. This innovative approach effectively captures complex volumetric effects, such as those created by fuzzy materials like a cat's hair or grass, as well as flat surfaces. The representation is constructed solely from RGB images, enabling real-time rendering and animation using traditional animation tools. The example showcases the ability to animate both Buzz and the kitten, altering their original pose while maintaining high-quality rendering. Unlike sugar, this method realistically renders very fine and fuzzy details, such as the kitten's hair covering Buzz's legs. Figure 2 illustrates the visualization of the thickness of the frosting layer on an example scene. The thickness is represented by varying brightness, with a brighter value indicating a thicker layer. Our method automatically adjusts the thickness of the frosting layer based on the material properties of the scene. For instance, it builds a thick frosting layer for fuzzy areas like the fur of the red panda plush, and a thin layer for flat surfaces such as the table or the floor. This adaptive approach allows for a more efficient distribution of Gaussians in the scene, allocating more in areas requiring detailed volumetric rendering. The paper demonstrates that using an adaptive thickness not only enhances performance compared to a constant thickness but also reduces artifacts during mesh animation. In this presentation, we will introduce three key concepts: Gaussian splatting, mesh, and differentiable rendering. Gaussian splatting is a technique used for rendering complex scenes by distributing Gaussian functions across the scene. It is particularly useful for its ability to handle high-frequency details and its computational efficiency. Mesh, on the other hand, is a structure composed of vertices, edges, and faces, commonly used in 3D modeling and rendering. It is known for its flexibility and precision in representing complex geometries. Differentiable rendering is a method that allows for the computation of gradients in rendering processes, enabling optimization and learning in rendering tasks. This technique is crucial for integrating with Gaussian splatting to enhance the realism and accuracy of rendered images. The paper introduces Gaussian frosting, a novel approach to 3D scene representation. It builds on the strengths of 3D Gaussian splatting, 3DGS, which enables fast and high-quality rendering with complex light effects. However, 3DGS has limitations in scene editing due to its unstructured and disconnected Gaussians. Gaussian frosting addresses these limitations by providing a hybrid representation that is editable as a mesh while maintaining or even improving rendering quality. Figure 3 illustrates the process of scene composition using frosting. By employing mesh editing tools in Blender, we successfully integrated various elements from different scenes, A, to create a completely new scene, C. Additionally, we modified the poses of the characters through the rigging tool in Blender, B. This approach, akin to surface-based methods like sugar. 11. Not only facilitates scene editing and compositing but also enhances the rendering of intricate volumetric effects and fuzzy materials, such as hair or grass. In the field of image-based rendering, IBR, various methods have been developed to create new images from a set of given images. Volumetric IBR methods, such as neural radiance fields, NeRF, use a multilayer perceptron to model a continuous volumetric function of density and color, enabling high-quality rendering. However, improvements in efficiency and memory usage are still being explored. Surface-based IBR methods, particularly those using triangle meshes, are popular due to their efficiency in rendering but face challenges in capturing fine geometry. Hybrid IBR methods aim to combine the strengths of both volumetric and surface-based approaches, often using implicit sign distance functions for geometry regularization, though real-time rendering remains a challenge. The 3D Gaussian splatting method represents a scene as a large set of Gaussians, each defined by a mean and a positive definite covariance matrix. The covariance matrix is further parameterized by a scaling vector and a quaternion for rotation. Additionally, each Gaussian has a view-dependent radiance characterized by opacity and spherical harmonics. This method allows for extremely fast rendering by splatting 3D Gaussians into 2D and blending them based on opacity and depth, offering a significant advantage over volumetric rendering methods like NeRFs. The initialization of this method involves using a point cloud from an SFM algorithm like CalMap to set the initial Gaussian parameters, which are then optimized to match the ground truth images using a rendering loss that combines pixel-wise L1 distance and a structural DSIM term. Figure 4 illustrates the process of creating a layer of Gaussian frosting. Initially, a Gaussian splatting representation is optimized using a rendering loss without additional constraints, allowing Gaussians to position themselves freely. These are termed unconstrained Gaussians. Subsequently, these Gaussians are regularized to align with the true surface of the scene, and a mesh is extracted to serve as the foundation for the frosting layer. The misalignment of surface-aligned Gaussians is utilized to identify regions requiring more volumetric rendering. Search intervals are constructed around the mesh's vertices, and the density function of the unconstrained Gaussians is employed to refine these intervals, resulting in the frosting layer. Finally, a novel, densified set of Gaussians is sampled within this layer. The Gaussian frosting creation method involves three main processes: the forward process, the backward process, and the frosting optimization. In the forward process, we start by optimizing an unconstrained Gaussian splatting representation to allow Gaussians to position themselves. We then apply the regularization term from sugar to align the Gaussians with the real surface and extract a surface mesh from the Gaussian splatting representation. The backward process involves building a frosting layer around the extracted mesh, defining inner and outer bounds for the layer, and parameterizing the Gaussians within this layer. Finally, the frosting optimization ensures that the Gaussians are properly initialized and optimized within the frosting layer. Figure 5 presents a comparison of meshes extracted using sugar from the Shelley dataset, both without and with our improvement that automatically adjusts the octree depth D and Poisson reconstruction based on the scene's complexity. Our technique, shown at the bottom, significantly reduces surface artifacts across many scenes, such as holes and ellipsoidal bumps on the surface, when compared to the default values used in 11, which are shown at the top. Figure 6 illustrates the process of defining the inner and outer bounds of the frosting layer. This layer is crucial for volumetric rendering, especially in areas with fuzzy materials like hair or grass. The bounds are determined by introducing two values, in and out, for each vertex of the base mesh. These values create two surfaces that define the layer's limits. The process involves considering both unconstrained and regularized Gaussians to ensure accurate thickness estimation. The search interval G is derived from the regularized Gaussians, ensuring that the isosurfaces close to the scene's surface are considered. This method helps in accurately defining the frosting layer, which is essential for realistic volumetric rendering of fuzzy materials. Figure 7 showcases the application of frosting in rendering complex scenes. The first row presents the renderings, the second row displays the recovered normal maps, and the third row shows the estimated frosting thickness. Notably, the frosting is thick on fuzzy materials like hair and grass, which is expected, and very thin on flat surfaces such as the table and the fourth column. This demonstrates the effectiveness of frosting in adapting to different surface complexities. Figure 8 presents close-up views of fuzzy materials from the Shelley dataset, comparing the reconstruction quality of vanilla Gaussian splatting and frosting. The center image shows the results from vanilla Gaussian splatting, while the right image displays the results from frosting. The comparison highlights that frosting significantly outperforms vanilla Gaussian splatting in rendering quality, particularly in handling challenging fuzzy materials. This superior performance is attributed to frosting's more efficient densification strategy, which targets areas requiring volumetric rendering more effectively. The experimental evaluation of Gaussian frosting involved calculating standard performance metrics such as PSNR, SIM, and LPIPS, and comparing these against several baselines. The evaluation was conducted on challenging datasets containing both synthetic and real scenes. In synthetic scenes, Gaussian frosting was tested on the Shelley and RF synthetic datasets, outperforming other methods including 3D Gaussian splatting. For real scenes, the method was evaluated on the MIPNRF 360 dataset, tanks and temples, deep blending, and a custom dataset of smartphone captures, demonstrating competitive performance against unconstrained Gaussian splatting. Figure 9 showcases examples of animation achieved with frosting. Specifically, it demonstrates the successful animation of a sculpture, as depicted in the left image, using the rigging tool available in Blender. This example highlights the animation capabilities of frosting, emphasizing its effectiveness in bringing static objects to life through dynamic movement. Figure 10 illustrates the comparison between using a constant thickness and our adaptive thickness strategy for the frosting layer. Our adaptive method is crucial for maintaining optimal rendering performance while preventing artifacts during scene editing. The right image demonstrates that a constant, large thickness can lead to artifacts when animating a character. Specifically, Gaussian's position near the right knee of the knight incorrectly reconstruct the right hand, causing noticeable artifacts when the hand is moved. Table 1 presents a quantitative evaluation of rendering quality on the synthetic datasets Shelley and RF synthetic. The results show that frosting outperforms all other methods, including non-editable models that focus solely on rendering quality. Specifically, frosting achieves the highest scores in PSNR, SSIM, and LPIPS metrics. This superior performance is attributed to frosting's ability to more efficiently densify Gaussians by targeting challenging and fuzzy areas, unlike unconstrained 3D Gaussian splatting. The table provides detailed comparisons with other state-of-the-art methods, highlighting frosting's significant advancements in rendering quality for synthetic datasets. Table 2 presents a quantitative evaluation of rendering quality on the MIPNRF 360 dataset, focusing on methods that recover an editable radiance field with explicit meshes. The table highlights that frosting achieves the best performance among all editable methods, demonstrating competitive results compared to NERF methods and vanilla 3D Gaussian splatting. Key metrics such as PSNR, SSIM, and LPIPS are used to compare the performance of various methods, with frosting consistently showing superior results in these areas among editable methods. Table 3 presents a quantitative evaluation of rendering quality across real scenes from tanks and temples, deep blending, and a custom dataset. Our representation, frosting, demonstrates superior performance among surface-based methods and maintains competitive results against unconstrained 3D Gaussian splatting and other non-editable methods. The custom dataset comprises 4 scenes captured casually with a smartphone: Sleepy Cat, Buzz, Red Panda, and Night. This evaluation underscores frosting's efficacy in handling diverse real-world scenarios, showcasing its ability to deliver high-quality renderings even in complex and varied lighting conditions. Table 4 presents an ablation study comparing 2 methods for computing the octree depth in Poisson surface reconstruction. The first method uses a predefined depth of 10, as in 11, while the second method employs an automatically computed depth. The study demonstrates that the automatic depth selection technique not only avoids mesh artifacts but also results in equivalent or superior rendering performance with significantly fewer triangles. This optimization is crucial for enhancing the efficiency and quality of the frosting representation in complex scenes. Table 5 compares various strategies for determining the thickness of the frosting layer in rendering tasks. The study evaluates the rendering performance, measured by PSNR, in both synthetic and real scenes. Key findings include that an adaptive thickness method outperforms constant thickness methods, especially in scenes with varying surface complexities. Additionally, the use of unconstrained Gaussians in refining the thickness is crucial for achieving optimal performance. The table highlights that while a large constant thickness can enhance performance in scenes with fuzzy materials, it negatively impacts performance in scenes with flat surfaces, leading to artifacts during scene editing. In conclusion, the proposed surface representation is both simple and powerful, offering significant advantages over existing methods. A key method for extracting this representation from images has been introduced. However, the implementation has limitations, such as the piecewise linear deformation model and the larger size compared to vanilla Gaussian splatting models. Future work could explore more sophisticated deformation models and compression techniques. The frosting representation is expected to be useful beyond image-based rendering, potentially in broader computer graphics applications for real-time rendering of complex materials. Thank you for watching.